Welcome back to the video series on integration and differential equations. Today we're going to work on the exponential form. So here's our key formula for this section. If we want to integrate e to the u with respect to u, we will get e to the u plus a constant. For our first example, let's find the following integral. Here's a tip for getting our integrals into this exponential form. To make our integral look like exponential form, we typically want to let u equal the exponent on the e. So in this case, let's let u equal 8x, since that's the exponent on our exponential. Du would be 8 dx. And now we can take a look back at our integral and see what we've accounted for. So this e to the 8x, we'll be able to rewrite that as e to the u. And now we want to figure out how to rewrite dx in terms of du. So let's put dx on this side, and then we'll ask ourselves, okay, what operation is going to take us from the second line to the third line? Well, we're dividing by 8, so du over 8 is the same thing as dx. And with that, we can rewrite our integral. So let's say the original integral is equal to the following. We've got the integral of e to the 8x can be rewritten as e to the u, and the dx can be written as du over 8. So I'll put that 1 over 8 out in front of the integral. Okay, at this point we've got a nice example of the exponential form. To integrate e to the u with respect to u, we're going to get e to the u plus c. So let's continue our work up here. We are going to get 1/8 of e to the u plus a constant, and then finally we'll go back to our original variable. So 1/8 e to the 8x plus c. If you like shortcuts, we can develop a shortcut for this type of problem that we just did. In general, if you're trying to integrate e to the kx with respect to x, that's going to come out to e to the kx over k plus a constant. Now, it's important, especially when you're using a shortcut like this, to be aware of what the restrictions are. So k in this context can be any constant, it can be any real number other than 0. So as long as you're putting a numerical value other than 0 in here, so like k value 2, k value -4, k value -pi, or something like that, the shortcut would apply. So let's put a box around that, and I'll show you a couple of quick examples of the shortcut. So for example, if we wanted to integrate e to the 3x with respect to x, 3 is a constant that's not equal to 0, so the shortcut would apply. We'd get e to the 3x over 3 plus a constant. So you can see that's the same pattern that came up in our first example. We were integrating e to the 8x, we got e to the 8x over 8 plus a constant. The shortcut could work as well if you had a fractional coefficient in the exponent there. So if we were integrating, say, e to the x over 2 with respect to x, well, 1/2 is our value of k here, so the shortcut applies. We'd get e to the x over 2, and then according to the shortcut we wanted to divide by k. So dividing by 1/2, that's the same thing as multiplying by 2, so it would look like 2 e to the x over 2 plus a constant. And then I would point out that if we integrated something like e to the x squared dx, shortcut would not apply. So shortcut only applies when you've got a number times x in your exponent, would not apply to e to the x squared, and in fact e to the x squared is a tricky function to integrate, so we won't worry about integrating that here. Let's try a second example. Let's find the integral of dx over x squared e to the 1 over x. Here's a second tip that will help you with integrating these exponential functions. The tip is to get the exponential in the numerator before substituting. So notice that right now we've got the e to the 1 over x sitting in the denominator. We'd like to move it up into the numerator, and we'll be introducing a negative exponent when we do that. It's going to be much easier to substitute once that exponential is up in the numerator. So let's rewrite our integral. In the numerator, we've got e to the negative 1 over x dx, and we'll leave the x squared in the denominator. Okay, so now that we've got the exponential in the numerator, it's more clear what the power actually is on the e. It's actually the power minus 1 over x, and that's what we're going to be substituting. So we'll let u equal minus 1 over x. And if you want, you could rewrite that. That's negative x to the negative 1. If we rewrite that more concisely, and now we can calculate our du. So derivative of negative x to the negative 1, that's going to be positive x to the negative 2, and we'll turn that into a differential. Okay, so if we rewrite this, we're saying du is equal to dx over x squared. And let's take a look up at our integral. Okay, so looking at this integral here, which we've rewritten, we're going to be able to rewrite the exponential. That's e to the u, and then this dx over x squared, that turns out to equal du. So we're all ready to go in terms of rewriting our integral. So let's continue our work up over here. We're going to say this integral here is equal to the following integral. We've got e to the u du. So that looks perfect. That's the classic example of our exponential form. According to our key formula, we're going to get e to the u plus a constant, and we can go back to our original variable. U was minus 1 over x, so we've got e to the negative 1 over x plus a constant. And that's our final answer there.